So hello and welcome to another Andy's Workshop video. In this video we're going to take a look at this little item that I got on eBay. It's a voltage regulator module from a server. Now I thought it looked interesting because A, it only costs about £6, and B, it's probably got some very high quality components on it because it'll be designed, it's probably going to be a buck regulator that will be designed to supply one of the voltage rails either for a CPU on the server motherboard or perhaps for the memory. In any case, it's likely to be very high quality and probably extremely stable as well. I thought it'd be good to have a look at it and see if there's anything I can make it do, and perhaps we can build it into something useful. Anyway, the first thing I think we should do is have a look around the board itself. So we can see straight off that it's made by a company called Artisan, and this side is dominated by the heatsink. If we just tilt it up, I can see a row of tantalum capacitors there attached to these big golden fingers. Clearly identifying those as some part of the output, or some part of the power system anyway. It's going to be either output or ground. Can't tell what's going on there at the moment until I get this heatsink off. I can see a MOSFET under there. That's definitely something we'll be taking a look at when I get the top off. And if we look at it from the other side, I can see big inductor there. That's going to be the power inductor, and there's a MOSFET, a TO220 there, screwed to the top of the heatsink. It's the bottom of the heating, sorry, and it's covered by the manufacturer's label there. So we'll have that off and we'll have a look underneath later. The other side of the board, this looks like the control circuitry. We'll identify those chips and we'll see what's going on there. And there's some very interesting features on here that we'll try and get into. Right, that's the power input. I can tell that because the fuse there, that little white component, it's definitely a chip SMD fuse. So that identifies that as the most likely candidate for power in. This is interesting here. These these rails here, they're fixed to a big plane here, and they appear to be bridging vias. They're obviously to enhance the current capacity of this thing. But if I just tilt it and have a look underneath, I can see that each one of them bridges a set of vias. So I think what they're doing there is obviously giving the current a clear path to the golden fingers. Where it can make its way out to the board, which definitely increases my confidence in the design of this thing. It looks really well made, and I'm looking forward to playing with it. So let's get that heatsink off the front and let's have a look underneath it. Okay, slight change of plan. I couldn't get the damn heatsink off. It's easy enough to get the screw out of there, obviously enough. I've got that off, that's not a problem. But the heatsink is also fixed down by these little silver heads you can see here, which are actually the top of some poles, which you can see was one there. There's four of them in total, one there, one over there, sorry, three of them, but they go all the way through. They're fixed to the heatsink and they go all the way through to the board on this side, where they are actually soldered in place, and they completely defeated the attention of my solder sucker to get those things out. And I think that's because all the heat that the solder sucker applied just went straight up the pole and into the heatsink, where of course it was lost. So change of plan then, we'll just deal with this thing by looking at the interesting part, which is all the circuitry on this side. And really all that's on there anyway is a bunch of capacitors, inductors and the power MOSFET. They would have been kind of interesting to look at in a way, but there's not a lot there. I mean, you can see a row of ceramics there. It's either input or output filtering, and you can see the tantalums there, which are performing the same function in either input or output. Sorry about the autofocus. So what we'll do is we'll take a close look at the chips on this side and see if we can identify what these little golden fingers are going to be doing, because they probably aren't anything to do with the power output. And we'll see if we can drive this thing and make it do something useful. Okay, so I've found the datasheet for the main IC on this board, this one here, and it's an Intersil HIP 6004B, and as expected it is a buck converter, or rather it's all of the parts that you need to orchestrate a buck converter. It's not one of the highly integrated parts that does everything on board that you can find these days. It's actually quite configurable. But the first thing we're going to do here is do some buzzing out of the golden fingers here versus the pins on the chip, because we want to find out where the voltage in is, we want to find out where V out is, and of course ground. And we have the pinout for this particular IC, so it should be easy to do. So let's get started on that. Right, so I've got my meter set to the diode test, continuity test mode, so it should buzz when I press these together, which it does. These particular probes have got pogo pins on the end of them. They're really quite useful for probing very small surface mount pins here. So let's see what we can do. First of all, let's go for ground. According to the data sheet, pin 11 is ground. So let's get one there. Nope. And let's move along. Nope, no sign of ground there. Let's see if it's on the other side. I'll have to reach underneath for this. Oh, hello. Yeah, that's ground. And the next big one along is ground. Oops, let go. And let's have a look at the end. Nope. It appears the end one is not ground. Let's just have a look on the other side. See if I can get a better look. If you look on the other side, that's how it is. Big pieces here. So it appears we've got ground here, and not ground there. Let's have another look. Oh no, I must have had a bad contact earlier on. I have a better contact now. So we have ground all down the other side there. That's good news. Okay. Okay, next up, let's go for VCC. I said earlier on, this was the prime suspect for VCC because this is obviously a fuse. So let's have a look with the buzzing out. So pin 18, according to the data sheet, is VCC. Let's drop a pogo pin onto that. And, oh yes, no surprises there. Let's see if it's anywhere else. And, no, and no. Okay, so we've only got it VCC here. That's good. Okay, so now we know where the voltage input is and we know where ground is. The last of the interesting blocks of pins are these here. Sorry, not that one, these two here. And it's going to be the output here. I'm almost certain of it, but we should always verify our assumptions. Now, if you look at the typical circuit for a boost or a buck converter in this case, you will always see that there's a big inductor in series with the output voltage. And if we look around here, we can see in the power circuitry that there's a great big inductor here and there's a little one over here. So my bet is that this the bigger inductor is going to be in series with wherever the output voltage is. So let's just buzz that and see. So I've got a pin on the inductor. It doesn't matter which end of the inductor I'm probing here. And let's touch that. Yes, that is the output, and so is that. So now we know where all the the major stuff is. The last one I really wanted to check is pin 12 on this little HIP 6004. Pin 12 is P good, which is power good. Now that's an indicator to any kind of monitoring circuitry that the converter is working as it should. It's an open drain output, so the your circuitry that you build around it needs a pull-up, but it should be directly connected. I bet it's directly connected to one of these little fingers here. So let's have a check. So we've got pin 10, 11, 12. That should be P good there. And let's have a little look around. Not on there. That's surprising. Let me just verify in the data sheet if I've got this right. Yeah, pin 12 is P good. Very surprised to not see that. Maybe it's on the other side. There's some fingers there. Sure I've got a good contact. Oh, there it is. I must have had a bad contact. Yeah, that's a dead short. So P good is there. So we've identified one of the little golden fingers. The rest of them, I've no idea. I've actually gone over this before. And I can tell you that they're not directly connected to any of the pins here. So we're going to have to, I think, get down to some electrical testing, power this thing up and see what comes out of these pins. Right, I've rigged up a bit of a hack here. I've just connected my power supply to the suspected, or well, now tested, input voltage and ground there, just using simple wads of paper to insulate the wrong side of the crocodile clip from coming into contact with something that it shouldn't come into contact with. Now, if we look at the data sheet, we can see that this particular chip is rated for 5 and 12 volts. I'm going to go and test the lowest one first. So my power supply is set to 5 volts. I've clamped in the ground probe here to the negative probe from my meter, and I'm just going to adjust the camera so you can see the meter itself. What's up there? So what I'm going to do now is just switch the power supply on. Okay, it's now on, and I'm going to probe the output and see what happens. That's not good, is it? 0.3, and it's jumping all over the place. I don't think that's working. Okay, so I'm going to switch the power supply off and dial the voltage, input voltage, up to 12. Let's see what happens there. It's a bit finicky. Okay, so we're on 12 volts now. I'll switch output to enable, so it's now running. I'm going to touch the output rail here and see what happens. The meter's measuring. 3.3. Ah, that's more like it. 3.3320. And very stable indeed, according to the meter. It's not jumping around anywhere. Oh, it's within one digit at the end. That's excellent. Okay, so 3.3 is a very usable voltage. I quite like this. Of course, there's no load on this thing, but because it's you know, a CPU power supply, presumably, this thing ought to be really stable under load. So what I'm going to do now is I'll switch the little gadget on here that you can see. That's my iTech DC electronic load. And we'll apply a varying load to this little power supply, and we'll see how it copes. Right, this test is even more of a hack than the last one. I've switched back to the stronger standard keysight probes that you get with the multimeter rather than those pogo pins, because I only needed those for probing SMD outputs, and they're quite delicate, so I didn't want to clamp them in like this. So what we've got now is we've got the output of this device connected directly into my DC electronic load. Let's have a look up here at that. So there it is, and the meter is clamped in as well, and it's also measuring. So the meter is measuring the voltage directly at the output of this power supply, and the iTech electronic load is obviously measuring the voltage at its own inputs here. After the current has passed through these leads, which are not the fattest of crocodile leads either, so I would tend to trust the keysight. I trust the keysight anyway because it's just a damn good multimeter versus what we see here. But we can see with no load, the meters are pretty accurate. The iTech is almost following the keysight to within one significant digit. So my power supply is currently showing a quiescent current draw of about 100 milliamps. Now what I'm going to do here is dial in. Let's go apply constant current. We've got constant current selected here at 100 milliamps and see what happens. The thing's not switched on yet. Okay, so switch the output on, and it is on. Oops, my mistake. Yeah, okay, so it's now on. It's 100 milliamps. Okay, no worries. And we're showing 3.32 here and 3.33 here. So let's dial up the current and see what we get. I'll just try and keep my fingers out of the way of the camera's view of the display. Now my power supply has a limit of 3 amps output, so I have to stop there anyway, even though I don't know what the maximum that this power supply under test can deliver. I know that my bench power supply can only deliver 3 amps. So now we're up to 400 milliamps, and looking at the keysight, there's very little changing in the way of the voltage output there. It's very stable. A few significant digits changing, but a few of the least significant digits changing. But we're still seeing 3.32, 3.33 fairly stably. We're up to 1 amp now, and the iTech is showing a lower voltage now than the keysight. I expect that is because of losses in the cabling here. So I tend to believe the keysight, because these are big fat probe cables. They're very nice. I think there might actually be a sense input on the back of this thing, but I'm not sure. Anyway. Let's go up 1.2, 1.3 amps, 1.4, 1.5. We're still showing stable, 3.3, 1.6, 1.7, 1.8. Up to 2 amps now, 3.30, 3.31 on the keysight, still looking good under load. My bench power supply is actually showing a draw of 0.7 amps, so that's not under too much stress. Remember, this is a buck converter, so I can actually deliver more amps out of the power supply than my bench power supply is going to deliver in. Go up again, 2.5, 2.6, 2.7, 2.8, 2.9, and we have 3 amps. I'm tempted to stop around here. We're still showing a good voltage, by the way, up on the keysight, 3.29, very stable. If you're looking for a 3.3 power supply, this is pretty damn good. and my bench power supply is showing power in of 1 amp, and if you do the constant power equation, you find out it's power in versus power out, and you could actually work out what the losses are in this thing. So I think I'm going to stop there. Don't know whether this thing's getting hot. Let me just see if I can get my finger underneath it. The old finger test. The heatsink is warm. It's lukewarm, I would say. That's definitely not under much stress at all. 3 amps isn't causing it much bother. Shall I go a bit further? Yeah, why not? I'll keep my finger on here, and if I shout out loudly, it's because it's suddenly got really hot. 3.2, 3.3. Let's go up to 4 amps. 7, 8, 9, 4. And the load regulation's still looking good. We look at the key site there, 3.28, 3.29-ish. Still looking very stable. Should we go further? Yeah, why not? Let's go up to 5 amps. My finger's not burning, by the way. Still feels good. 4.4, 4.5, 5, 4.6, 4.7, 4.8, and we're showing a little drop on the key sites meter now. I could actually chart this, couldn't I? We could see the load regulation start to go off as the current goes up, and you can hear the fan in my bench power supply come on there. Bench power supply is delivering 1.6 amps, and we're getting 5 amps out at 3.27. Very stable still. My finger is not getting any warmer than it was. I'm going to stop there. I think that's enough for this particular test. Let's bring it back down again slowly. We can watch the output voltage go up slowly as we go. I should really note these numbers down and chart them. We can see what the regulation's like. But I can't be bothered at this moment. Yeah, let's go down a bit faster. And the output voltage climbing back up again. 65.2, 0.1, and we are off. Good. Okay, so this is good. I think the next thing I need to do, now this is a nice power supply. I mean, I'm satisfied with the performance. What I want to do now is just have a quick probe around those golden fingers. I'm not going to bore you with this. I'm going to probe around those little fingers and see if I can see what they're up to. So I shall be back in a second. Okay, so what I did here to help me identify these pins is to photograph the board and print out a copy of it, blown up to a rather large size. And I'm afraid I've had pretty much mixed results with the investigation of what these pins do. The big fat ones are labelled here, we know what they are. I've determined that this one here, I've labelled these A to F. The first one on the left I've determined is driven to 3.3 volts, same as the output. No idea why. Next one is not connected. The next one is driven to 12 volts, which is the same as the input, even though it's not a dead short to the input there. Again, I can't determine why. D is P good. I know that's definitely the power good output signal. E is driven to 12 volts. No idea why, unfortunately. And the F pin is not connected to anything. Now I did the same on the other side as well, so let's have a look at that one. So here we have 2 NCs not connected. G and H, I've labelled those. I don't know what that does, unfortunately. I haven't worked it out yet. And K, I haven't worked out what that does, but we'll return to these two actually in a second. J is not connected, so the only interesting things on this side are I and K, here and here. What I have determined, I measured the impedance of these to ground, and they're 50 ohms, which is really suspicious, so I suspect they're inputs rather than outputs. They do appear to be floating. So what I actually tried to do was apply varying resistances from these pins to ground, just to see what would happen, and it appears to affect the output voltage by a small amount. I basically fitted up a potentiometer to each one, and in turn it was a 22k linear pot that I had, and I just moved it around slowly, and I could see the output voltage changing as I did it in a small way. It's smaller changes with pin K. This one here, this one was changing by about 10 millivolts per change that it made, and this one was pin I was changing by about 7 millivolts depending on the position of the potentiometer. So I think I and K here are some kind of perhaps compensation mechanism for the output voltage under load. Maybe if I had to guess, I would say the output circuitry monitors the monitors the level of the output, and if it falls below or above a particular range, then it might use these pins to bring it back into line. I don't know that for sure, that's just a guess. If anybody has any idea what these pins do here, or even what these outputs are doing over here, then please do drop a comment or an email somewhere. I'd love to know what they are. I think I've now reached the end of my investigation of this board. I could use it as is. I'd like to build a power supply around it. It's really easy to get a little socket for one of these things, place the power supply board into it, and just run out connectors to the edge, and I'd have a really stable 3.3 power supply. But without knowing what these pins do, the unknowns here and the unknowns there, I'd be missing some of the features. So I'm going to hold off building something just to give time for feedback, and hopefully maybe somebody out there can let me know what these pins are going to be actually doing. And if you have any ideas, let me know, and I'll set up a test and we'll see what happens. Okay, well, that's the end of the video, and thank you very much for watching.